Have you ever stopped to think about how your voice can literally fly across the planet in a split second? Or how astronomers can listen to the faint echoes of the Big Bang? Well, it all comes down to this hidden language that powers pretty much everything, and that language is signals. Today, we're going to decode these invisible messengers.
So here's the game plan. We'll start with the basics. What even is a signal? Then we'll break down its DNA. After that, we'll get into the huge divide between analog and digital, touch on a few of a signal's unique personalities, and finally, we'll see how this stuff is literally running our world. Let's jump in.
All right, let's kick things off with a little brain teaser for you. I want you to think about three totally different things: your smartphone, your own heartbeat, and a massive earthquake. What on earth could possibly connect all three of those?
The answer, believe it or not, is super simple. They all use signals. Every single one either creates or depends on signals to get information from one place to another, and that physical thing that carries the information, that's exactly what we're going to break down.
Okay, so let's start with the most basic question of all. What is a signal, really? And to get to the heart of it, we're going to use a really simple analogy. At its core, a signal is just information in motion. But here's the really important part. A signal isn't the information itself, it's the carrier. Think of it like a delivery truck. It's a physical thing like a change in voltage, a flash of light, or a sound wave that we tweak and modify to carry a message. Let's make this way more concrete. Imagine you're stranded on a desert island. You can't just think a rescue message to a passing ship, right? You have to put that message into some kind of physical form. So you could wave a flag. That's a visual signal. You could yell for help. That's an audio signal. Or you could light a big fire and make a smoke signal. In every case, you're changing something physical to send your message. And that, my friends, is a signal. Okay, so we've got the what. We know what a signal is. Now let's look at how they're actually built. We're going to deconstruct a signal's DNA, because it turns out just about every signal you can think of is made from three basic building blocks. And those three building blocks are amplitude, frequency, and phase. Seriously, once you get these three, you can pretty much understand any signal out there. You've cracked the code. First up, we have amplitude. This is just how strong or intense the signal is. The easiest way to think of it is just volume. The difference between you whispering and you yelling, that's a change in amplitude. Simple as that. For an electrical signal, it would just be the difference between low voltage and high voltage. Next up is frequency. And if amplitude is about strength, frequency is all about speed. It's how fast the signal is vibrating or repeating itself. With sound, this is what we call pitch. A high, squeaky voice has a really high frequency, while a deep, booming bass voice has a very low frequency. It's even the number on your car radio. When you tune to 98.7 FM, you're just tuning into that specific frequency. And finally, we have phase. This one's all about timing. It tells you when a signal starts, usually compared to another signal. The absolute best way to picture this is to imagine two people clapping. If they clap at the exact same time, they're in phase. But if one person's clap is just a little bit late, they're out of phase. This is a huge deal for stuff like noise-canceling headphones, which basically create an out-of-phase sound to wipe out the original noise. Pretty cool, right?
Okay, I want you to pay close attention here, because this next idea is absolutely, positively crucial for understanding the world we live in. We're talking about the difference between analog and digital signals. Before we get into the nitty-gritty, let's just use a super simple metaphor. I want you to think of an analog signal as a smooth, continuous ramp. You can stand at any possible height along that ramp, right? Now, think of a digital signal as a staircase. You can only be on one specific step or another. There's no in-between. So, let's really break this down. Analog is that smooth ramp. It captures every single tiny little detail, which is why music lovers go crazy for the rich, warm sound of vinyl records. Digital, on the other hand, is the staircase. It takes little snapshots of the information and turns it into numbers, usually just ones and zeros. This makes it incredibly clean and almost immune to noise, which is perfect for computers and the reason your MP3s sound exactly the same every single time you play them. Now here's the big takeaway. The real world, your voice, the temperature, light, it's all analog. But our computers, they are 100% digital. They speak two completely different languages. So how in the world do they talk to each other? Well, they need a translator, and that translator is called an analog to digital converter, or an ADC. Its job is to take that smooth, messy, analog reality and chop it up into the clean, numbered steps that a computer can understand. Now, it's not a perfect copy. You always lose a little bit of detail. But what you gain is a language our entire digital world can be built on.
So besides just being analog or digital, there are a couple of other personalities that signals can have.
that just help us classify them and understand how they behave. Let's look at two real quick.
First, you have periodic versus aperiodic. A periodic signal is one that repeats a perfect pattern over and over and over, like the steady tick-tock of a clock. An aperiodic signal, though, never perfectly repeats. It's always changing, kind of like the sound wave you create when you speak a sentence.
And then there's deterministic versus random. A deterministic signal is something you can predict perfectly. You can write a math equation for it. But a random signal, like the static or snow on an old TV screen, it's completely unpredictable. You have no idea what it's going to do next.
All right, we've gone through a lot of theory. Amplitude, frequency, analog, digital. But here's the payoff. Why should you care about any of this? Because once you start looking for them, you realize that signals are the engine running almost everything around us.
Just think about it for a second. An ECG at the hospital, that's just reading the tiny electrical signals from your heart. A seismograph? It's detecting the physical signals of an earthquake moving through the ground. Radar is just using bounced radio signals to figure out how far away a plane is. Heck, the show you're watching right now is nothing more than a massive stream of digital signals being turned back into pictures and sound. It's everywhere.
So if you take away just one thing from all this, let it be this simple idea. A signal is just a physical way to send information. If that information is smooth and continuous, like a wave, it's analog. If it's all choppy and coded into numbers, it's digital. That's really the foundation of everything.
And that leaves us with one final, kind of mind-bending question to chew on. We've learned to read the signals from our own hearts, from the deep earth, and from the edges of the universe. As our world gets smarter and more connected, what do you think will be the next great signal we finally learn how to read?